So I have. Can you see the screen?
Yes,
It's okay.
I see my
All right.
face.
So what is your question?
So I was actually doing the practice exams that were on Blackboard.
Ah, okay.
So I have questions on the first and second practice exam for exam 3.
Just tell me. Better.
Yeah. Okay. So for the first problem, it had the graph that was the cycle, like pressure and volume.
Oh, you're way ahead of the class.
Yeah. And I mean, I could just wait until
That's okay.
we cover this.
We will cover it, but there's nothing very difficult about it. So I'm going to give you an answer, and I think, yeah. So what kind of a graph is it?
It's a rectangle, so it the first, I guess, vertical line points up. And that's just the direction of the cycle. It's like a clockwise cycle.
Mm-hmm.
And then the bottom left-hand corner is labeled A.
Okay, so then B.
Yeah. A. Yeah.
B, C, D. All right. There are several possibilities depending on what we know, what we're looking for. But do you have a specific question about cycles in general?
Yeah, I guess my point is, how do I determine the change of internal energy and then the change in heat? I know work is just pressure times volume.
No.
No.
Not always.
Right.
In this case, so first of all, a cycle is an example of several processes happening one after another.
Mm-hmm.
And for each process and for the whole cycle, you can analyze these variables.
Right.
So in this case, you can analyze it for process AB, BC, CD, DA, and then for the whole cycle from A to A, for example.
Right.
So 5. Now, the work in general.
Mm-hmm.
If you use a graph, pressure as a function of volume, the work during a specific process in general is equal to area.
Right.
But as you said correctly, if you have a specific process like this, when pressure remains constant, in that case, area is just, pressure times delta V, height times base. So this is the work done for any process with constant pressure.
Right.
And you have two like this.
Mm-hmm.
This is BC and DA.
Mm-hmm.
But if there is no change in the volume, AB or CD, when there is no compression or expansion, there is no work done.
Right.
So now, for each process, doesn't really matter, A, B, C, D, whatever, for each process, you have some initial temperature and final temperature in general.
Mm-hmm.
And that is how we analyze change in the internal energy, because internal energy is proportional to temperature, directly proportional to temperature.
Mm-hmm.
Did you see an equation for internal energy before?
I feel like we did. I don't.
Well, yeah, but we didn't we didn't do an equation that relates it to the temperature.
Mm-hmm.
So,
but it was changing heat. or heat is the change in internal energy?
Well, heat is equal to the change in the internal energy of a system if there is no work.
Right.
But if there is work, so as I said today, Q equals delta U if there is no work. But if there is work, we have to add amount of work done by, well, us on a system.
Mm-hmm.
So this is the first law of thermodynamics, basically, the law of conservation of energy. And if we are looking for, well, again, depends what we know, what we don't know. Sometimes we know amount of heat. Sometimes we're looking for amount of heat. And in that case, we rearrange this equation, in one way or another.
Mm-hmm.
So in this problem, what do you know? What values are given?
So you're given a label on the axis. Point A is at V naught and P naught.
Mm-hmm.
And then B is at 3 times P naught.
Mm-hmm.
And then D is at 5 times V naught.
So you know volume, pressure, and
Yeah. And I know point A is 1,000 joules. It says P naught times V naught equals 1,000 joules.
okay, so they give you a number
Mm-hmm.
for this product.
Right.
Anything else?
It says that CV equals 3/2 times R.
CV equals 3/2 times R. Okay.
And that's it.
So this tells us how to relate the internal energy of this gas and the temperature of this gas.
Okay.
This is what we call, and we'll talk about it on Monday probably, a specific heat capacity of this gas at constant volume.
Mm-hmm.
In general, the relationship between how much energy the gas stores and the temperature of the gas is given by this equation.
Right.
And this number I is given, well, for you, but it could have been a different depending on the gas.
Mm-hmm.
It could have been a helium. So for helium, it's like just many tiny balls. So, but we will learn also that pressure and volume and temperature are related by this expression.
Mm-hmm.
This is the ideal gas law.
Right.
So if you combine these together, that tells you how to relate. Well, now we can. Energy and this product, PV.
Mm-hmm.
So in your situation, that's, I guess, all we need to know if you need to calculate the change in the energy, because you can calculate each energy. The energy for point A will be equal to 3/2 P naught times V naught, which is 1500. Because you just replace this product with 1,000.
Okay. Right.
And 1,000 over 500 times 3, 1,500 joules. And now you can repeat it for all other. So because internal energy at point B will be equal to 3/2 times, well, that's a new pressure times the same volume.
Mm-hmm.
So it's going to be 3/2 times P naught V naught times 3 because of this coefficient. So that's 1,500 times 3, 45. And then you do the same for C, for D. And if you want to calculate change, for example, A, B, right? So it's going to be energy at B minus energy at A, which is, now we know, 4,500 minus 1,500. 4 minus 1, 3. 300 joules. So this was an important piece of information.
Right. Okay. So that makes sense.
And then now, yes, ask the question.
Okay, so for then Q, it's just the sum of, or internal energy minus.
Yeah, Q equal, for Q you need W as well. You see, Q equals change in the internal energy plus work.
Okay.
So for example, QAB, what is it? That's delta U AB plus WAB work. But delta UAB is 3,000. And work is what? 0, because for this process, volume does not change. It remains constant.
So that's 3,000.
Yeah, of course.
Okay.
But if you go to the next process, and let's go to the next process. BC. This is V naught. This is 5 times V naught. This is 3 times P naught, correct? So Q from B to C, how much heat does the system absorb? The law says, yes, ask.
I was just going to answer. It's like the total area under, well, you have to find work first, which is the area under.
Well, doesn't have to be first. You know that it's 4,500 joules plus, and now you say, okay, yeah, we have to do the work, and the work is supposed to be equal to the area and now you can calculate the area because you know how to do this.
Right.
It's going to be 5 V naught minus V naught, the base times height, which is 3 times this. So 4,500 plus, you see, 4 times 3 times again this product. So 4,500 plus 12,000.
Okay.
And we get what? 16, 15.
Yeah.
That's it.
Okay.
And then you move on to the next process, So CD is easy because there is no work here. And then DA. Well, here you need to be careful because now your volume decreases. So the work is supposed to be negative. So QCD should be equal to change in internal energy CD, which is UD minus UC. But QDA should be equal to, no, because work is 0.
Right.
dA plus work for dA, and that's going to be, it's always final minus initial, so it's going to be this plus, and what do we have here? Well, again, it has to be pressure times change, and change now is again final minus initial. So it will give you negatives, okay?
Right. But that makes sense because it's a cyclical process.
Yes.
Okay.
If you want to calculate total work, for example, you have to do work AB plus work BC plus work CD plus work DA. That will give you the area of this rectangle.
Mm-hmm.
If you want to calculate total Q over the cycle, that's going to be same QAB plus Q plus Q CD plus Q DA. And same with internal energy, delta U for the whole cycle. But good thing about this is going to be zero for the cycle. Why?
Because
if you do this cycle,
right,
your initial and final temperatures are the same. So your initial and final energy will be the same.
Right.
So that's a good thing to know about the cycle.
Mm-hmm. Okay.
And of course, Q for the whole cycle should be equal to delta U for the whole cycle should be equal plus work for the whole cycle, and for the whole cycle this is 0.
Mm-hmm.
So for the whole cycle, Q is W always.
Okay. Good. All right, that makes sense. Thank you.
Good.
Okay. So the second problem was, again, it's like a multi-part problem. So you found a quantity of energy in the first part, and that was 4 times 10 to the 6th joules. And then the second part, it said, while providing the amount of heat energy in part A, the student was able to generate 50 watts of power to do work for 1 hour. How much work does a student do in 1 hour? And I might have just like assumed, since, power is work over time.
Power
right?
is work over time.
Yeah. So when they said 50 watts, I was just, for 1 hour. This might have, okay.
If the power is 50 watts and time equals 1 hour, you have to use 3,600 seconds.
Okay. So, but it doesn't have anything to do with the heat energy?
I'm sorry. First of all, this is power.
Power.
Yeah, not work. Work will be equal to power times time. Yeah.
Mm-hmm.
I'm not sure. Could you please again read the question?
Yeah, so it said, while providing the amount of heat energy in part A, which was 4 times 10 to the 6th joules, the student is able to generate 50 watts of power to do work for 1 hour. So how much work does a student do in 1 hour? So they're just...
Well, this, yeah.
So that's all I need is the 50 watts. It doesn't really have anything to do with the heat energy, right?
Well, at this point, no.
Okay.
If you know the power, doesn't matter how it's been produced.
Right. Yeah. Okay, so that was just my clarification question, because I was kind of confused, like, by that wording.
Well, yeah, it happens.
All right. Okay, I think that's it for now. Thank you.
Thank you.
Take care.
Have a nice day.
Thank you.
And let's see if there's anyone else. No, there is not. Okay.